Okay, guys, can you see my screen there? You should see like an introductory chemistry paper.
Yeah.
Okay, perfect. So again, this is kind of a very different layout to what you'll have, okay? So for your exam, it's each question is worth 25 marks, okay? You'll have 5 questions to pick from, and you'll have to answer 4 of them, okay? So you'll have a little bit of choice there. And they're more kind of specified on topics, so they're not going to mix in too many topics. So say one question will be on, I don't know, say one question will be on bonding, the next one will be on a titration question, and it'll all be, the whole question will be to do with that topic rather than mixing them, okay? So I don't want you to kind of get too bogged down and looking at this layout and going, oh, it's all over the place, because it's far different from what we're going to do. There's just little bits and pieces that are similar in terms of the questions, all right? Okay, so I'm going to start with this one here. So anything I have highlighted is are questions that will probably be examinable. All right. So we had this as part of your stoichiometry lecture. Okay, so this is lecture 4. And it was finding the percentage composition by mass of calcium in Ca3PO42. So what I recommend, sorry, I'm just going to increase the size there so you can see it. So in terms of any of these questions, all right, the very first thing that you should start out with is your molar mass of your substance. Okay, so whatever you're trying to calculate, I would start off by calculating the molar mass of whatever you're working with there. Sorry, no, let's get off this. Okay, so in terms of what we're working with here, we're working with Ca3PO42. So the very first thing you should be thinking of, right, I need to calculate the molar mass of that. Okay. Sorry guys, the formatting is kind of driving me demented here at the minute. Okay, so your molar mass of Ca3PO42. So what I'd start out with is just writing all of your elements down in a line. Okay, so all the elements that you have in your compound that you have to work out, I would list like this. All right, so it's very same thing of what we've done already. So what I would do then is I go to your periodic table and I would take down the period or the molar mass of each one of these elements themselves. Okay, so you will have a copy of the periodic table of elements in your exam. So all you have to do is look up the molar masses of each one of those from there. Sorry, I'm just looking at it for myself. Sorry, there's 2 seconds. It's acting up on me here. Okay, so we know oxygen is 16 grams per mole anyway, all right? Okay, so then for calcium, then it is our 40 grams per mole. And our phosphorus then is 31 grams per mole. All right, so then we're just going to multiply it by what we have of each one. Okay, so the number of atoms of each one of those elements that we have. So in terms of our calcium, then we have 3 atoms of calcium, okay, based on what we have in our molecular formula there. So I'm going to multiply that by 3. So whenever you see a bracket like this means that it's a group. Okay, so that means on that specific compound, you have 2 groups of what's called a phosphate. Okay, so you have 2 phosphate groups. What we need to take into account is that those 2 groups, we need to multiply everything within those brackets by 2 because they're 2 separate groups from each other. All right. So in total, in the whole molecular formula, we have 2 atoms of phosphorus, 1 on each group. Okay. For our oxygen then, so we have 4 oxygen atoms on each group. We have 2 groups, so we need to multiply that by 8. Is everyone okay with that so far, guys?
Do you always round up or round down accordingly? Do you know, say the phosphorus was 30.9 something and say the oxygen is 16.07 or whatever it is.
So in terms of your exam, I would use what's listed on the periodic table itself. Okay, so whatever I'd say
Yeah.
it will be the kind of 2 decimal places. If they're the 2 decimal places, I would use the 2 decimal places.
Okay.
Um, it's just I'm just kind of looking those up online just as I have them here, so I'm just getting the kind of nearest whole number. But whatever you're given in the exam on your periodic table, that's what I would use.
Okay. Thanks.
So if the oxygen will be like 15.99, would you use as a 15.99 or you would use as a 16 then?
I would use the 50 if it's listed on the exam as say in your periodic table is 15.99, I would use 15.99.
Okay, yeah, that's great. Thank you.
No worries. Okay, so I'm going to multiply each one of these out then. Okay, so you have your 120 grams per mole in total for your calcium. 31.2 then is 62 grams per mole in total for phosphorus. And then our 16 by 8.
128.
128, is it? Perfect, thank you very much. Okay, so then we're just going to add all of those together then. So 120, 62, and then 128. So we should be getting 310 here.
Yeah.
Okay, perfect. So for that alone, guys, I know it hasn't answered the question yet, but for that part alone, you will be getting half of the marks available for that. Okay, so if you just stop there, you would get 2.5 marks alone for that. Okay, so that's why I always recommend, even if you have no idea where to start the actual question, I would just always start with the molar mass of whatever you're working with, because you will get marks for that. All right. So in terms of your percentage composition then, so just as I'm kind of going along, and I'm going to highlight what slides these are in. Okay, so this is in lecture 4 on slide 14. Okay, so the percentage composition. Just if you're following along with the lecture notes, okay? I have no idea what that's coming up in Italian, but never mind. So, we're looking for the percentage composition by mass of calcium. Okay, so your percentage composition is your atomic mass of your element, whatever the element you're looking for here. Okay, so in this case it's calcium. You multiply it by the number of atoms of that element, and you divide it then by the molar mass of the compound itself. Okay, so your percentage composition looks a little something like this. Okay, so in terms of the top of that equation, we've actually already calculated that, okay? Up here. Okay, so if we're looking for calcium, so it's our 40 grams per mole, that's our atomic mass of our element. We multiply it by the number of atoms, which is 3, to give us 120 grams per mole. So we actually have that part covered there already. So that's what I'm going to fill in there, okay? Can everyone see where I got that from, yeah?
Yeah.
Perfect. So then I'm going to divide it then by what we just calculated. Okay, so that's our 310 grams per mole. Oh, I'm sorry, it's a percentage, so you multiply by 100, okay? So multiply by 100 to get into our percentage. So that should be 120 divided by 310 multiplied by 100. And for all of these guys, unless specified, I would round them to 2 decimal places. All right. So some answers will say like round to the nearest whole number, round to 3 decimal places. If it doesn't say it, I would always round to 2 decimal places. So in this case, I got an answer something like this. So I would always round that to 38.71. And that's your final answer for that one then. Is that okay, guys?
Yeah.
Simon, anyone have any questions on that so far? Are you all okay?
Okay, I think.
Perfect. So what I will mention here as well is just as I was going along, you'll see that I included all the SI units in the calculation itself, okay? So it's really important that if you're actually calculating something to make sure that you include the SI units all the way along. All right, so you'll see grams per mole mentioned here. You'll see it in the calculations up here. It just shows the examiner that you know exactly what you're trying to calculate at the end of those calculations, okay? Because sometimes if you're just showing random numbers, and particularly if you're not using the correct number, they can't award marks for it, okay? Because they don't know what you're working with. So what I suggest you do is every time you're writing out a calculation, just make sure you have the SI units included in it, and particularly in the answers as well. Okay, everyone happy enough with that then?
Yeah.
Yeah.
Okay, perfect. So I'm going to skip on down now. There's a couple of bits that we don't need here. Don't worry about that one. Yeah, so this one is one that would be appearing. Okay, so it's writing out the electronic. Oh no, sorry, never mind. Don't mind me. It's the next one. Yeah, sorry, it's this one. Calculate the number of protons, neutrons, electrons in the following. Okay. So this would be kind of related to your atomic structure and your bonding lecture notes, okay? So I'm just going to pull those up now when I have them. Okay, so this is kind of more related to your atomic structure notes. So I think that is lecture 2. Okay. I just want to get you the exact say for me your exact slide number, that's all. Okay, so it's kind of between it's kind of between slides 8, 9, and 10. 8, 9, and 10 on lecture 2. Okay, just so you have it for your notes. Okay, so the first thing what we're going to do then is we're going to first write our protons, our neutrons, and our electrons. Okay, so what we should have here then, guys, is your periodic table of elements open, okay? Because we're going to need it to work out your atomic number, your mass number, and so on. Okay, so what we have here then is your potassium. Okay, so it's K. So potassium's atomic number is 19. All right, so what the atomic number should tell you is the number of protons in the nucleus of an atom of potassium. All right, so that is your number there. That will always equal the number of protons in its nucleus. All right, so that's what I'm going to list there. That will never change. All right. Your neutrons then is going to be your mass number minus your atomic number. Okay, so just make a note of that. Okay, so your neutrons are going to be your mass number minus your atomic number, and your protons are your atomic number. And the way I always remember it is that if you're looking at an element on the periodic table, the larger, so it's molar mass, all right? So the mass number is the molar mass, and it's always the higher number. So if you have an element, and I don't know if you have your table of elements open in front of you, but if you are looking at potassium now, so potassium has a weight of 39 grams per mole. But that is also the number, its mass number. Okay, so the mass number is always equal to the molar mass. And it's always the larger of the two numbers that you see on its periodic table of elements, all right? So for potassium then, its mass number is 39. I'm going to take away the atomic number of 19. Okay, because in the nucleus of an atom, okay, you have neutrons and you have protons. So by taking one from the other, I know how many protons I have. So the difference between my total number and the number of protons should be my number of neutrons. So in that case, it's going to be 20. Does everyone see where I'm getting that from, guys?
Yeah.
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 Okay, perfect. Right, so your electrons here, this is where it's a little bit different, and that's why it's really important to pay attention to the signs or the charges. So these two are examples of the ones that are charged. So it's either that plus or that minus. All right, so that's really important. So what you have here then, so if that was a neutral element, okay, so if I just had a neutral element of potassium, okay, so a neutral atom of that potassium, it would be 19 protons and 19 electrons, okay, because your protons are, so they're positively charged. And your electrons are negatively charged. So if I had a neutral atom of potassium, those two would cancel each other out. So that means if I had 19 protons, I should have 19 electrons. But it's not the case here, okay? So I basically, that plus tells me that I have one additional positive charge. So can anyone tell me then how many electrons I should have?
20.
20.
18.
18, exactly, okay? So if I have 18 electrons, okay, and this is how you check it, that if I add, think of the protons as a plus, I have 19 pluses, 18 negatives. So taking one from the other, I have one additional positive charge. All right. So your final answer for that one would be 19 protons, 20 neutrons, 18 electrons. Is that okay, guys? I'll go through another example anyway, so we can get practice on it, but it's going to be the same thing over and over. All right. So in the exam, what I do is have your protons, neutrons, electrons. I'll get rid of all this. Okay, so we have zinc now, okay? So it's going to be the exact same method here, just using a different element, all right? So, okay, so our zinc there is 30, okay? So that has an atomic number of 30. And that your protons will always be the first one that you do, okay? So there's an atomic number of 30. Our protons are positively charged, so we should have 30 protons. Your neutrons in, so then in the exact same way we did the first example, all right? So our zinc has an atomic mass, or sorry, a mass number of 65. And then we're going to take away our atomic number of 30. Okay, so in the nucleus of the atom, we have neutrons, we have protons. If I know I have 30 protons, if I take that number away from my total, I should have the number of neutrons as well. Okay, so 65 minus 30 will give me 35. So in terms of what we just covered then, guys, so looking at my element that I have there, how many electrons do you think I should have?
Person.
Yeah, exactly. Okay. Because in this example, my zinc is not positively charged or negatively charged. So my positively charged protons are being cancelled out by an equal number of negatively charged electrons. So I should have equal amounts of both. Okay. So 30 protons, 30 electrons. Okay, so we'll go through that last example then, just to finish off this question. Okay, so fluoride then. So that is our ninth element on the periodic table. So we should have 9 protons there for our atomic number. Okay, so looking at the same element then, so where fluorine has a mass number of 19. I'm going to take away my atomic number just to give me my number of neutrons, and I should have 10 neutrons there. Okay, then, so just coming back up here, looking at the actual element itself. All right, so if I see a negative charge there, all right, so in this example up here, I had a positive charge. In this example, I have a negative charge. So what that means is that I have one additional negative charge. So in terms of how many electrons I have then, how many do you think I have based on that?
10.
10, exactly. Okay, and that's your final answer for your electrons, okay? So if you take your number of protons away from your number of electrons, it should give you one additional negative charge. And I will say that would be the same for any number of charges there. So say, for example, if that was, no, this one doesn't exist, but it's just an example, okay? So if that was 2 minus, that would mean 2 additional negative charges, all right? Which would mean that would be 11.
11. Yeah.
Okay? Because there will be some examples where you'll see 2 plus or 3 plus or 2 minus. And 3 minus doesn't exist, but it's either you have just the sign, so that means 1, or you have 2 minus, 2 plus, or 3 plus. But you do those in the exact same way. Okay? Is everyone happy enough with that, guys?
Yeah.
Perfect. Okay. Brilliant. So that question typically, so the marking scheme here is a little bit different because these are kind of the short questions on the introductory chemistry. For fundamentals of chemistry, they'd be worth a little bit more. So in terms of you'd often have 3 examples. So you'd have 3 different elements to work out, and each one of these is worth 1 mark. All right, so that would be worth 9 marks on our paper in regards to like 5 on this paper. Okay. So just by having your protons, neutrons, electrons for each one, there are 3 marks for each element, so 9 in total. Is that okay, guys?
Yeah.
Perfect. Okay, so we'll keep moving on then. Yeah, so again, this would be one complete question for our module, as opposed to a slightly shorter version on this paper. But they kind of cover the same topics, okay? So it's good to practice these. So I'm going to start off then with question 2. So this is kind of tying into our molarity. Okay, so just again, if we're just following along on our lecture notes, okay, so I think it's lecture 5. Yeah, so we're kind of tying into our solution stoichiometry here. Okay, so your dilution equation to be exact, okay? And that would be slide 12 on lecture 5. Okay, so just if you want to make a note for yourself as we're going through these, this would be lecture 5, slide 12.
Mm-hmm.
Okay, so this asks what volume of a 12 molar hydrochloric acid solution must be taken to prepare 750 ml of 0.2 molar HCl solution. All right. So I would just write down everything that I have of importance in a question when I have it, okay? So what we have is 12 molar, we have a volume of 750 ml, and we have 0.24 molar HCl as well. Okay, so what you should be thinking now is that this is a concentrated solution. Okay, so if you even look between the differences in your, sorry, I'll take the highlight off this just to make it easier. If you look at the differences in the concentration between your starting solution and the solution you're going to prepare, it's incredibly diluted in comparison. Okay, so you're starting off with a very concentrated solution and you're going to prepare a dilute solution from that. Okay, so you'll be able to tell that from the kind of big difference between the two concentrations there. And from the 750 mils, you're preparing that solution. Okay, so that's the one you're going to prepare via dilution of this concentrated solution. So I'm going to call that your volume of dilute solution. Everyone okay with that so far, yeah?
Yeah.
Okay. So what you should be thinking here then is your dilution equation. Okay, so it looks a little something like this. So it's your molarity of your concentrated solution multiplied by the volume pipetted of your concentrated solution is equal to the molarity of your dilute solution multiplied by the total volume. So we actually have 3 out of the 4 things here. So what we have to do is rearrange that equation and solve for what we're missing. All right. So this is why I find it handy to write all these down first, and then you can just simply input them into the equation then, all right? So your molarity of your concentrate there, okay? So that's going to be your 12 molar. It's always the larger of the two, okay? So your 12 molar HCl there is your concentrated solution molarity. Your volume pipetted, okay? So that's what the question asks for, okay? So you see it there, so what volume of this solution? We don't know that yet. So I'm going to call that X. That's what we're going to solve for. Your molarity of your dilute solution, then, so we're given that in the question, that should be 0.24 molar. And then the volume that we're going to prepare for that is 750 ml. Everyone okay with that so far, guys?
Yeah.
Perfect. So what we're going to do then, we're just going to rearrange this whole equation to get X on its own. All right, so what we should have over here is that if you want to get X on its own, you bring the 12 molar across to divide on this side. All right, so it's multiplying over here. You bring that across the equal sign. The 12 molar is now going to divide. So this is what we should be left with here. And then we just need to calculate that out.
That should be 15 mil then.
15 mil, perfect, yeah, that's great. Okay, so your X there should be 15 mil. And that's your final answer for that question. So it's kind of a clue that you should be using this, your molarity of your concentrated and your dilute, so your dilution equation. Okay, so the one that's listed on slide 12 of that lecture is that if you're given 2 solutions with 2 different molarities and you're given 1 volume, all right? So this question will either ask you, they might give you, they'll say 12 molar HCl, 15 mil was pipetted into 750 mil, and you'll have to calculate the new molarity. You do that in the exact same way, just labeling X as something else. So it's either the volume that you use to make the solution, or it's the new molarity that you're going to prepare. But it'll be the exact same method each time. All right. But it should be giving you a clue that if it's giving you 2 solutions and 1 volume, or 2 volumes and 1 solution, you should be using that equation. Is that okay, guys?
Yeah.
Okay, perfect. So I'm going to keep moving on then. Yeah, so this is an empirical formula question, part B. All right, so I'm going to put this exam paper up on Moodle afterwards, and I'll highlight the ones we went through just so you have them, okay? But in terms of what we're covering here now, it is the empirical formula. I'll just go double check the slide. Yeah, so your empirical formula kind of goes from slide 20 to slide 20 to 25 of lecture 4. All right, so it kind of gives you an example there, but I'm going to go through this one because this is kind of typical of what you'd see in an exam. All right. Okay, so you're given a sample. Okay, so a sample of lead arsenate, an insecticide, I wouldn't worry about that, contains this amount of lead, this amount of hydrogen, this amount of arsenic, and this amount of oxygen. All right. It says calculate the empirical formula of lead arsenate. Now, in terms of the fundamentals of chemistry exam, you will be given each one of the symbols at least for these. Okay, so it'd be very rare that they just tell you to kind of go find them on the periodic table. All right. So in case I'm just going to write them in here for you now. Okay, so obviously hydrogen is H. Arsenic then is okay, so that is AS, and oxygen is obviously RO. Okay, but it would be very rare that they would do that. They'd give you the compound or the element, and then they give you the symbol for it, so you don't have to go searching through the periodic table. Okay, is everyone okay with that so far? Yeah. All good?
Yeah.
Okay, perfect. Okay, so we're just going to start off then. Okay, so your step 1 here. We're going to get each one of these into moles. Okay, so convert grams to moles. Actually, scratch that a second. So step 1, we're actually going to just take down all the molar masses of each element. Okay, so take down molar mass of each element. In this case, you don't have to calculate them, but we're just going to list them all out so we have them to hand. Okay, so we have AS and oxygen. Okay, so your lead then. Okay, so this has a atomic mass of 207 grams per mole. Okay, so you'll find that from your periodic table. Okay, so hydrogen has a mass of 1 gram per mole. Arsenic then has a mass of 74. I think, no, sorry, 75 rounded up, so 75. And oxygen then is 16 grams per mole. Okay, so again, I took these directly from the periodic table. Okay, so step 2 then is converting the grams to mass, or convert the mass to moles, I should say. Okay, so we're going to start out with your lead then, and we're told that we have 1.3813 grams of lead. So before I do that, okay, so just remember your triangle, okay? So if you have a mass value and you want to convert it into moles, the moles is the mass divided by the molar mass. Okay, so on that triangle that we've kind of practiced with, okay, your mass is on top, the moles are on the left-hand side of that triangle, and your molar mass is on the right-hand side. So if you cover the mass, or the moles is what you're trying to calculate, so cover that over, it tells you to divide the mass by the molar mass. So we're going to do that for each one of those here first, okay? So for PB, what you should have is our 1.3 0.813 grams divided by our 207 grams per mole. Okay, is everyone getting 0.00667?
No.
Okay, so what did you get there?
Oh no, it could be okay. Yeah.
Yeah, all good?
Yeah, the same. Yeah.
Okay, perfect. Okay, so we're going to do that for each one. So each one of these examples, okay? So we have our lead, our hydrogen then is our simple one because that is going to be 0.00672 grams divided by 1 gram per mole. Okay, so obviously that's just going to be itself. So 0.00672. Our arsenic then. So that is 0.4995 divided by 75. Okay. Does anyone just want to call out what they got for that one then? Just so I can double check we're all on the same page.
0.00666.
0.00666?
Yeah.
Perfect. And then our oxygen then is our 0.4267. And that's going to be divided by our 16 grams per mole.
Zero point zero two six 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 eight seven five. That's too many, so I'd say
So
we round it up
0.02.
666.
0.02666 moles. Perfect. Okay, that's fine. We'll leave it there. Is everyone okay with that, guys? Everyone can see where we're getting those values from, yeah? Yeah, all good?
Yeah.
Okay. Yeah. So now we're going to find the mole ratio between each one. Okay, so what we do here is that we identify the smallest mole and divide each one by that. Okay, so in terms of our smallest mole amount there, so it's 66. So it's actually our arsenic there.
Yeah.
Okay, so we're going to divide each one of these by arsenic. So I'm just going to copy that again. All right, so I'm bringing these down. Okay, so if I had for my lead, okay, if I had 0.00667 moles, and I'm going to divide that by 0.00666 moles, that's going to come out as roughly 1. Okay, so for these, I would definitely round them up to the nearest whole number because that's what we're looking for. All right, we're looking for the simplest mole ratio between all of the elements. So that divided by that will give you roughly 1. For our hydrogen, then I think that's the same. Okay, so we're going to have 0.00672 moles divided by 0.00666 moles to give us 1. Our arsenic then is obviously just going to be itself divided by itself. So that will definitely give us 1. And our oxygen then, so it will be the biggest one here. Does anyone want to call out what they got for this one?
4. It's gonna be 4.
4. Perfect.
Yeah.
Okay. So everyone can see where we got those from, guys. Yeah, so we have the simplest mole ratio between each one now. Okay, so this one turned out to be fairly simple. It's just 1:1 is to 1:4. Okay, so what I would do at this stage, so your step 4. Okay, so your step 4 is to write out the empirical formula. Okay, so what I do for this, I'm just going to write all of the elements that we have. Okay, so we have and leave a space between them. Okay, so it's going to be our lead, our hydrogen, our arsenic, and our oxygen there. So where these mole amounts now come into play is that we have to write them as subscripts next to each number. All right. So for lead, we had 1. Hydrogen, we had 1. Arsenic, we had 1. And oxygen, we had 4. So then to tidy that up, then we just get rid of the ones. So that will be something like this. Okay.
Yeah.
Is everyone happy enough with that, guys?
Does the order you put down the elements matter at all?
No, not necessarily for this. Okay. So if you
Okay.
had to write out like a, what am I trying to say? If you had to write out a specific molecular formula, yes, but for the empirical formulas, when you're calculating these, it's just better to write it out as you're giving them in the question because
Okay.
it's going to be the same thing anyway.
Yeah, no problem. Thanks.
All right. All right, guys, perfect. So what I'll do is I'll move on to part C here. I'll balance the reaction equation, okay, because that's going to give us practice of balancing chemical equations. We might take a little break then, maybe just for 5-10 minutes, and then I'll finish off part C then, because it kind of goes into more of our stoichiometry questions then, all right? Is that okay?
Yeah.
Perfect. Okay, so I'm moving on to part C here. Okay, so they kind of normally give you a spiel at the start. Okay, so you have solid lithium hydroxide is used in space vehicles to exhale carbon dioxide from the living environment. And then we have the reaction mechanism. So what they normally start out these questions off is balancing the reaction equation. So what I recommend you do, and it's kind of what we practice already. Okay, so I would write yourself a table in the exam on your exam sheet, okay? That's something like this. So you have your left and right. And then I'm going to list all of the elements that we have on each side of the equation, all right? So I have lithium here, coming from there. I have oxygen, I have hydrogen, and I have carbon. And that's all I should have, okay? Because I can't create anything on the right-hand side. So I should have everything covered there as your elements, and then we have the left and the right-hand side. Okay, so the first thing you do is just count each one of the elements that you have off the bat, all right? Because that's going to help us determine what we have to balance first. So on the left-hand side of the equation, I have 1 lithium element, okay, coming from here. And on the right-hand side, I have 2. I have Li2 on this side, all right? My oxygen then on the left-hand side, so in total, I have 1 oxygen atom here and 2 for my carbon dioxide. So that's going to give me 3 in total. On the right-hand side, then I have 3 over here and 1 for my water. That's going to give me 4. My hydrogens then, so I have 1 on the left-hand side and then 2 on the right-hand side. And my carbons then is 1 and 1. Okay, can everyone see where I got those from? Yeah, I'm just counting them on each side of the reaction.
Yeah.
Okay, so I'm going to start out with lithium here first. Okay, so can anyone suggest what I have to do to the left-hand side of the equation to make sure that they're equal?
To put it in 2 in front of lithium.
Exactly. Okay, so I'm going to just write that in bold. So if I put a 2 in front of the lithium there, all right, that is now balanced by lithium. So in the exam, what I would do is I would physically cross out the 1 and write the 2 next to it. Okay? And you can say that that lithium is now balanced. Now, the thing that we have to double check is that how did that affect the rest of the left-hand side? And does it balance the right-hand side now? Okay? So moving on to your oxygen then, okay, so now in total I have 2 from here. So 2 from my lithium hydroxide there and 2 from my carbon dioxide. So by doing that, I actually balance my oxygens as well. And I actually balance my hydrogens as well, okay? So I have 2 hydrogen atoms on this side, 2 hydrogen atoms on the right-hand side. So I can cross that out. And I have 2 on my left-hand side here too. And my carbons are always balanced, so I didn't need to go near them. So I can say that's the balanced chemical equation. Okay, so that one was easy enough, but it's just always handy just to double check each element, okay? Because sometimes if you add a coefficient in front of a compound, it can throw other things off. So it's just always handy just to double check them by crossing them out and going through them each time. Is that okay, guys?
Yeah.
Okay, perfect. So what we might do here is that we might just take even just a 5-minute break. Okay, so if you want to just take some time until about 25 past 6, and we'll come back and we'll finish off that question then. Is that okay?
Yeah, perfect.
Perfect, guys. Thanks a million. Perfect. Okay, I'll just start sharing the screen again in 2 seconds. All right, guys, can you see the question we were just on?
Yeah.
Perfect. Okay. All right, so we're into kind of our conversion of mass to moles questions now. All right. So it says, what mass of carbon dioxide can 1 kg of lithium hydroxide absorb? So again, what you should be thinking before you do any of these questions, okay? So you're going to calculate your molar mass. Okay, so like I said before, even if you can't get the rest of the question, if you work out the molar masses of what they're asking you for, you will be awarded marks for that. Okay, so even if you can't continue on with the conversion, at least you have something that was in a step in the right direction. All right. So what I do is I work out the molar mass of everything that is listed in the question. Okay, so I'd work it out for carbon dioxide, and I'd also work it out for lithium hydroxide because we're going to need it, right? So, sorry, I keep zooming out too much. Okay, so what we have here then. So I'll work it out for lithium hydroxide first. So for lithium hydroxide, we have lithium, we have oxygen, and we have hydrogen. Lithium then, so we have a sorry now, just looking for my lithium periodic table.
7.
7.
7, isn't it?
Yeah.
Yeah, perfect. That's great. Thank you very much. Okay, that's 7 grams per mole. Okay, so oxygen then, as we've had already, 16 grams per mole. And then hydrogen is 1 gram per mole. So you'll notice it's kind of a lot of these questions are just repetition of the same thing over and over again. All right, so once you kind of get the step practice with the steps, it actually becomes the very same question over and over again. Okay, so for this one here, just looking at its formula, we have one of each. Okay, so we don't need to multiply that by anything. So I can just skip on to calculating the total. Okay, so that will be 17, 17, so that's 24. Okay, so that's for my lithium. Okay, so I'm going to do the exact same thing then for my carbon dioxide. So in this case, I only have carbon and oxygen. My carbon is 12 grams per mole. My oxygen is 16 grams per mole. I have one atom of carbon. Okay, so one atom of carbon up here. But I have two atoms of oxygen to give me 32 grams per mole. So now I just need to get total there. So we should have 44 grams per mole there. Okay, everyone okay with that so far, guys? Yeah?
Yeah.
So there's our two molar masses for what we need. Okay, so your step 2 then. So we're going to convert the mass given to moles, okay? So okay, again, so in the exam, what I recommend you do is that for your triangle to convert mass to moles, I would write that somewhere, even on the exam paper itself, just so you have it, okay? But from that, okay, so if we were trying to work out the moles, it would be mass on top, moles on the left, molar mass on the right. So moles is equal to the mass divided by the molar mass. And we were told we have 1 kg. So there's this question, and we won't be dealing with it much, okay? But just so I can show you for this question, all right, that can you see that all of the molar masses are grams per mole?
Yes, we have to convert that, isn't it?
Exactly. So we have 1 kg. Sorry, no. So 1 kg of our lithium hydroxide. So we need to convert that into grams. Okay, so that should be 1,000 grams. Because if you went ahead and just used 1 kg, you'd be off by a factor of 1,000. All right, so if you did, we probably won't come across that too much, but just in case, if you see an SI unit that's different to what you're working with, you just convert it and then go ahead. Okay, so for that, then we have 1,000 grams divided by our lithium hydroxide molar mass. Okay, so that's going to be 24. Okay, so 1,000 divided by 24. So it's 41.66.
Yeah.
Perfect. Okay, so now we have a mass or we have a mole amount of our lithium hydroxide. Okay. So we need to equate that back to, well, we have lithium hydroxide, but it's asking for carbon dioxide. So what we should be looking at here is, so step 3, okay, so it's the moles. So moles of carbon dioxide. And we're going to use the balanced chemical equation for this. So this kind of ties into where we were looking at the ratio between them. Okay, so if I just come up here, I'm actually going to copy this down just so we have it so I don't have to keep scrolling back up and down. Okay, so that's our balanced chemical equation. Okay, so we worked that out in the very start. And we're looking at the ratio between these two. Because that's what we're not worrying about our products in this case. We're only looking at lithium hydroxide and our carbon dioxide. Okay, so can someone tell me what the balance chemical, so the ratio between those two are?
2 to
Yeah.
1.
Exactly. Okay, so we have 2 to 1. So what that means is two moles of our lithium hydroxide reacts with 1 mole of CO2. But in this case, okay, we don't have 2 moles. Okay, so we have 41.66. Okay, so we scaled up that reaction an awful lot and used 41.66 moles. So can anyone tell me what the new ratio is now?
20.83.
20.83?
Yeah.
Perfect. Yep, because it's for every 2 moles of this, we have 1 mole. So to get 20 moles of CO2, you divide that by 2. Okay, so I'm just going to say divide by 2. Okay, so that will give me 20.83 moles of CO2. Your last part of that then, so your step 4 then, because if we go scroll back up to the original question, it said what mass of carbon dioxide? Okay, so we have a mole amount, which is great. So now we just need to convert it back into mass. Okay, so looking at your triangle again. So if we were looking for mass, that would tell me to multiply the moles by the molar mass. Okay, so we have 20.83 moles. And we worked out the molar mass of carbon dioxide at the very start. So that is our 44 grams per mole. And all we need to do is just multiply that out and we should have our answer.
960.52.
Say that again, 960?
916.
Oh, 16,
Point,
sorry.
yeah, 0.52.
52. Yeah, perfect. And that is our final answer for that one. Okay, so you'll notice that it's the exact same thing over and over again. All right, so you start out with obviously your molar masses here, work out what you have. You have a mass that you're converting into moles. You equate the 2 moles together and then you work backwards to calculate the mass of whatever it asks you for. Okay, so it's almost the same format each time. Molar mass, converting mass to moles, looking at the ratio, then working back the way. All right. Everyone okay with that, guys? Does anyone have any questions on that so far? No? All good? Okay, so I'll keep going then on just part 3. Okay, so it says how many moles of our lithium carbonate. Okay, so we're looking at our product now. I'm just going to copy our balanced chemical equation down so we have it. Will be produced if all of the 1 kg lithium hydroxide is used up. So we've actually done an awful lot of the groundwork for this question up here. All right. But as I said, you'll probably be hearing me saying this in your sleep now, but it's calculating the molar mass of what you have or what you're working with. Okay. So we'll have the molar mass, and in this case, it's going to be Li2CO3. Okay, so we're looking at our product now. Okay, so we have lithium, carbon, and oxygen. So our lithium is our 7 grams per mole. Okay, multiply by 2 because we have 2 atoms of lithium here. Your carbon is 12 grams per mole, multiplied by nothing, okay, because we have 1. And our oxygen then is 16 grams per mole by 3. Okay, to give us 48 grams per mole in total. And then we should have 14 for lithium here. Everyone okay with that, guys? Everyone can see where I'm getting those from?
Yeah.
Perfect. Okay, so for my lithium carbonate then, I just need to add all these together. So I have 14 grams per mole by 12. So that's our 26. Okay, so 26 plus 48. So it should be 74. All right.
Yeah.
Perfect. So it asks then, it said how many moles of lithium carbonate will produce if all of the 1 kg of lithium hydroxide is used up. So we've worked out the moles already. So I'm going to copy this directly down because we've found out how many moles are in 1 kg of lithium hydroxide already in the top question. All right. So I can actually skip on now to working out how many moles of this will form by looking at step 3. Okay, so mole ratio. And now I am looking at lithium hydroxide to my Li, my lithium carbonate. Okay, so can everyone see that that's 2:1 again, yeah? So I have 2 moles of my lithium hydroxide and it forms 1 mole of product. Yeah, everyone can see that?
Yeah.
Perfect, okay. So that is going to be our 2:1. So again, it's actually going to be the exact same thing. So we have 41.6 moles lithium hydroxide. And we're going to divide that then by 2 to get my moles of lithium carbonate. So what I'll have there is 20.83 moles. Because if I had 2 moles of lithium hydroxide, I'd form 1 mole of lithium carbonate. But I have 41.66 moles, so I should form 20.83. And that's my final answer for that one then. Is that okay, guys? So again, you'll notice it's the exact same thing over and over again, nearly at this stage, all right? So it's just asking you for different molecular formulas each time. Okay, so in terms of the last question then, so just bear with me 2 seconds, I just want to write it back to our lecture notes. Okay, so this is on this question in particular. So part 4 of that exam paper relates to our lecture 4 stoichiometry, and that's slide 19. All right, so it says how many oxygen atoms will be in this number of moles of lithium carbonate? Okay, so the first thing we need to do is our number of our number of molecules of lithium carbonate. Okay, so like we said on slide 19 of that lecture, okay? So recall from that then that if we had 1 mole of anything, so 1 mole is equal to 6 by 0.2 by 10 to the power 23 atoms or molecules. Okay, so that's Avogadro's number. So it's kind of what I said about the mole, okay? So the mole is just another way of describing a number, okay? So like I said, if I had 12 molecules, you know I'd have a dozen. If I had half a dozen molecules, you know I'd have 6. So if I have 1 mole of molecules, it's this number of molecules. Okay, so it's just another word to describe a number. So if I had 1 mole of lithium carbonate, for example, I would have this many molecules of it, and that would be job done. Okay. But I don't. Okay, so I use 20.83 moles. Okay, so if 1 mole is equal to this, what do you suggest I do to work out how many molecules I actually have? Sorry, what was that?
Multiplies by average Avogadro's.
Exactly. Yeah, so you're just going to multiply your number of moles by the number of molecules. Okay, so what we should have there then is and then 20.83. Okay, so what I'm getting here then is, so I should have 1.25 by 10 to the power of 25. Everyone see where I'm getting that from, yeah? Okay, so it's your number of moles. So I'm just going to write that there. So number of moles multiplied by Avogadro's number. So that's what we're working at there. All right, so it would be very simple if I had 1 mole of whatever I had, because that would just be that. But I just need to work out how many is in 20.83, so it's just as simple as multiplying them together. All right, so that's your number of molecules. But this question specifically asks for oxygen atoms. Okay, so what I need to do then is I need to look at how many oxygen atoms I have per molecule, and then multiply it by the number of molecules that I have. Okay, so I'm going to say is number of oxygen atoms. So it's number of oxygen atoms per molecule multiplied by the number of molecules. Which makes sense, okay? Because if I had 1 molecule of lithium carbonate, I would have a certain amount. But I don't have 1 molecule, I have this. So you have 1.25 by 10 to the power 25 molecules. So I need to multiply them together. So from looking at my molecular formula then, how many oxygen atoms do I have on each formula? So if I were to show you this here.
3.
Yeah, exactly, okay. So that's 3 atoms of oxygen per molecule. And then I've already worked out the number of molecules is this number here, say 1.25 by 10 to the power 25. Okay, so you'll find that you just need to multiply that number by 3. So 3 on each molecule, and then multiply it by the number of molecules. So in that case, then it would be
3.75 by 10 to 24.
yeah, perfect. So it's our 3.76. So 3.76 by 10 to the power of 25 oxygen atoms. And that's your final answer for that one then. Is that okay, guys?
We have to learn off Avogadro's number. or be given to us?
No, you'll have to learn that off, but it's just, even if you don't remember 6.02, 6 is fine. Okay, so it's
Ah.
just this part here you'd have to learn.
Will we get a temp marks for like right?
What was that, Kira? Sorry?
Sorry for laughing. I'm lost. I said, will we get a temp marks for just writing that out? And if we leave it at that? Because I don't think I'm gonna remember all
For
that.
for which part now?
Oh, all of it.
Oh yeah, so you'll be
Just from
given a
that,
temp
just from the last bit. It's
this
only
part here,
the
is it?
yeah, yeah. I'm completely lost.
Okay, so I'll go through it again for you there, all right? Just no, this question is kind of, it's more one of the more advanced of the questions, all right? So it's kind of rare that this one will come up anyway, but I just wanted to cover it just in case it did. But what you will get attempt marks for here is that, like, you've obviously worked out the number of moles from the previous parts of the question, all right? So say that's where I got that number from, that 20.83. What you get attempt marks for here is that if you were able to say this, okay, so 1 mole is equal to Avogadro's number. So you would probably get attempt marks for that. You get attempt marks for writing down the number of moles. I'm probably getting this far, I would say. Okay, so in a question like that is worth, like, a lot of those steps were worth kind of 5 marks. That would kind of be the end of a question that would be worth 3 marks at all, if even. So if you were to able to write down even this part here, that will get you 1 mark, maybe 1.5. Is that okay?
Yeah, thanks.
No worries at all. So guys, that's kind of I've pinpointed like a lot of the questions that will kind of be fairly similar between the fundamentals of chemistry and the introchemistry papers there. Okay, so what I will say is that even though we've gone through them and they're kind of similar enough calculations, these ones are a little bit more advanced than what will be coming up on, say, our papers. I just wanted to show you these because there is very little examples of the papers for fundamentals chemistry. And if we're able to kind of work through these, to some extent, like we're kind of getting the basis of it covered, it will be much easier for the exam as well. Okay, because these ones are a little bit more advanced. But they're kind of good examples because they show an awful lot of the calculations in the same question. So yeah, is there any other questions on that so far then, guys? No? All good? Okay, so what I might do at this stage, we just have a little bit of time until I'll finish up maybe around 7, 5 past 7. I won't, like, I know we started a little bit late, but I don't want to bombard you with too much revision either. And I have this recorded anyway, so I'll throw this up onto the Moodle page afterwards. But what I will do is I'll switch back on to maybe, I'll have to stop sharing the screen and just bear with me 2 seconds. I'll switch back onto the fundamentals of chemistry paper, and then I will maybe do 1 or 2 examples of that then. Is that all right?
Yeah.
Perfect. Okay. Okay, so you should be able to see the fundamentals of chemistry, semester 1, year 1.
Yeah.
Perfect. Okay. Yeah, so you'll see kind of very, very much like similarities between what we have. All right. So I'm going to start, I'll start question 2 here. Okay. And even if you don't get it finished, I'll pick it up for next week. But sorry, no, let's get all this stuff out of the way. Okay, so what we have here is a question very similar to what we just did. Okay, so it says the development of large-scale production of acetyl salicylic acid, so the active ingredient in aspirin, is believed to be the beginning of the modern pharmaceutical industry. Wouldn't worry too much about that. It says in the laboratory, salicylic acid, so 3 grams, is reacted with an excess amount of acetic anhydride. Wouldn't worry about too much. All we need to take from that is that we're working with salicylic acid and we have 3 grams of it. Okay. So it says how many moles of salicylic acid are used in this reaction. So what I would start off doing, and again, you're gonna be sick of me saying it, but it's your molar mass. Exactly. Okay. So molar mass, and what we're working with here is salicylic acid. C7H6. Okay, so the exact same way we've done before, okay? So list all of your elements that we have. Okay, so you have carbon, hydrogen, and oxygen. So carbon from your periodic table, 12 grams per mole, multiplied by our 7. Okay, so we have 7 carbon atoms in our aspirin there, or salicylic acid. So we'll multiply it by 7. Hydrogen then is our 1 gram per mole by 6. Oxygen then is our 16 grams per mole by 3. Everyone happy enough with that? Yeah, everyone. So it's the exact same thing as what we've done already.
Yeah.
Okay, so 12 by 7 then. So that is our 12 by 7 is 84. So 6 grams per mole. And we should have 48 in total then for our oxygen. Okay, so 48 grams per mole. Okay, so our total molar mass then will be 84 plus 6 plus 48, which is 138 grams per mole. All right, so that's your step 1 there, done and dusted. So your step 2 then is your converting the mass to moles. Okay, so in the exact same way we've just done it before. Okay, so from your triangle then, your moles is your mass divided by molar mass. So we're given the mass in the question, okay, so that's going to be our 3 grams. So our 3 grams, and we've just worked out the molar mass as 138 grams per mole. Okay, so is everyone getting a final answer here of, we'll say 0.022?
Yep.
And that is our C7H6O3. And that's the final answer for that one, okay? So that didn't ask us to go any further for that question. All right. So in terms of the kind of the marking scheme for our module then, so you'll see that's worth 5 marks. So even if you got down as far as working out the molar mass for that question, that would give you 2.5 marks. And then step 2 then would be your other 2.5 marks. Is that okay, guys?
Yeah.
Perfect. So I'll finish off then just the end of this question. Okay, so what mass of acetyl salicylic acid can be made from this amount of salicylic acid? So I'm going to this paper is a little bit weird because it didn't give you it gave you kind of the diagram of the reaction. But if you look here, so our salicylic acid is our reactant, our acetyl salicylic acid is our product. Okay, so you'll see the difference there. So it's asking basically how much product can we form if we use that amount of our reactant. Okay. So I'm just going to write it next to it just so it's a little, so this is our reactant we're looking for here that we've just worked out. All right, so we're going to look at our, and what I would do again is your molar mass of what you're given. So that is your C9. So you'll find this is like the starting point for an awful lot of these questions, okay, is working out your molar mass. Okay, so are you guys comfortable enough that if I just I'll just list that here, or do you want me to go through the calculation again? Do you want me to go through the calculation, or are you just happy enough for me to call it out?
I'm happy to call out.
Yeah.
Okay, so right there. Yeah, so this one should be 180 grams per mole. Well, it's done in the exact same way that we would have done previously, okay? Okay, so now we have our molar masses of what we need, okay? So now we need to look at our ratio between our reactant and our product. Okay, so we have our C7H6O3 is our reactant, and our product is acetyl salicylic acid, but that is our C9H8O4. Okay, so just a reminder where I'm getting those from is just under here. Okay, so you'll see it in the reaction there, C7H6O3, C9H8O4. Okay, so we've actually already worked out the moles of our C7H6O3 or a reactant. Okay, so I'm going to put those down here. Oh, sorry guys, just you scroll back up here. So from here, okay, it's a little bit different for this one, but we have a 1:1 reaction here. All right, so we don't see any subs or the coefficients in front of any of these molecular formulas, okay? So it's a 1:1 reaction here. Okay, so salicylic acid, 1 mole of this will form 1 mole of your product. So that's our mole ratio there, okay? So 1:1. So if that's the case, then how
It'll be the same.
exactly? So we form 0.02 moles of our product. Okay, so that's how many moles that we form. It's a 1:1 reaction. So if we only use up 0.022 moles of reactant, we'll only form 0.022 moles of our product. Okay, so just looking back on the question itself then. So that says what mass of acetyl salicylic acid. Okay, so your last point there is just we need to convert moles to mass. Okay, so you had your triangle. So mass is your moles multiplied by the molar mass. Okay, so we've just worked that out as 0.022 moles. And our molar mass then that we've worked out in step 1 there is 180 grams per mole. Okay, so your final mass then, and answering the question is what mass of acetyl salicylic acid? That should be 0.022. So what you should be getting here, guys, is 3.96.
Yeah.
Perfect. So that is your final answer for that one. And that was another 5 marks. So I'd say if you'd gotten down as far as maybe, say, step 1 and step 2, that would give you 3 marks. And your final 2 marks then would come from the last little conversion there into your grams. Is that okay, guys? Okay, so the last little part of that then, so just your last little 3-mark question at the end. Sorry, it's going to write on me. It's your percentage yield. Okay, so just in terms of our, so this is on lecture 4. Just gonna double check that now. So I think it's at the end. Oh no, sorry, it's actually in lecture 5. It's on lecture 5 and it's our slide 3. Okay, so lecture 5, slide 3. Okay, so your percentage yield calculation then is your, we call it your actual yield or the actual mass that we've gotten over your theoretical mass. Or as we call it, like what we should have gotten. And then it's multiplied by 100 because it's a percentage. Okay, so the question asks here then, if 2.7 grams of acetyl salicylic acid is formed, calculate the percentage yield. Okay, so our percentage yield then, so we're told that we did this experiment, all right, so we got 2.75 grams. And what we should have gotten is the mass that we worked out up here. Okay, so can everyone see where I'm getting that from? Yeah, so 2.75 grams was given in the question, and we're told, and we worked out that we should have 3.96. Okay, so your theoretical mass is what we should have gotten. We should have gotten 3.96 grams. When we did the experiment, we only got 2.75 grams. So our final answer then for percentage yield is 2.75. Okay, so in terms of this, you should be getting around 69.44.
Yep.
Perfect. And that is your final answer for that one then, guys. Okay, is everyone happy enough with that? So you'll see, I suppose, in the introductory chemistry onto your fundamentals of chemistry, there's not as many steps in it, and there's more marks given for each step. Okay, so in terms of you have your molar mass, again, if it was in the first paper that we covered, that might be only worth 1 mark. In our papers, there were 2.5 if you calculate that directly, and then you can take it on from there. All right. But it's the very same, you'll see it the very same thing over and over again, in terms of the content itself. All right. So does anyone have any questions on that then before I finish up? Not for the moment, anyway. Okay, so what I'll do is I'll stop sharing the screen. Just bear me 2 seconds.